Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing to look at the SN1 and SN2 nucleophilic substitution reaction mechanisms. However, in this section, we're going to actually look at some special alkyl halides, the allylic and benzylic halides. Now, allylic halides are those halides that have a halogen represented by X here bound to an sp cubed hybridized carbon. Now, in order to be allylic, the sp cubed carbon must be attached to a C double bond C. And indeed, you can have primary allylic, secondary allylic, and tertiary allylic, as designated by the carbon attached or carbon bearing the X or the halogen. Benzylic halides are similar to allylic in that the halogen is also bound to an sp cubed carbon. But in this case, the sp cubed carbon has an aromatic ring attached to it. The sp cubed carbon bearing the halogen determines whether you have a primary benzylic, secondary benzylic, or tertiary benzylic alkyl halide. Notice because they are attached to sp cubed carbons, these are alkyl halides. Now, their chemical behavior is rather unique, so we're going to look at them separately from the alkyl halides we looked at in the SN1 and SN2. If you recall, in the SN1 and SN2 key features, allylic and benzylic halides are not listed in the previous podcasts. However, if they were, they would be considered often the most reactive in SN2, often reacting faster than even methyl halides, and in the SN1, often reacting faster than even tertiary alkyl halides. Now the question is, how can we account for the chemical behavior of allylic and benzylic halides in the SN1 and SN2 reaction mechanisms? One thing to note is that the tertiary allylic and benzylics, I'll draw a box around them, shown here, will not react via SN2. And do you know why? Remember, the SN2 mechanism involves backside, nucleophilic backside attack, and because of that, it must attack the carbon from the backside, and steric hindrance plays a big factor. Typically, tertiaries cannot be attacked in this manner. So for steric hindrance reasons, or due to steric hindrance, tertiary allylic and benzylic do not go SN2. They will go SN1. However, all other allylic and benzylics, primary and secondary, can go SN1 or SN2 very well, and often better than some of the best alkyl halides. Again, leaving group plays an important role here. So we need to understand why. Why are these allylic and benzylics so reactive under SN1 conditions, and why they are also so reactive under SN2 conditions? So let's begin looking at SN1 conditions, and we'll start with the allylic halide under SN1 conditions. So allylic halides. Okay. Allylic halides. Well, the first thing in the SN1, the step 1 is the ionization step. If we start with a simple allylic halide, there are no surprises in the SN1 reaction. Step 1 is ionization or carbocation formation, as usual. And we'll start with an allylic bromide. And as usual in step 1, I could draw a transition state for the first step. This is the slow step of the reaction, remember. And the bromine begins to leave. So this is my transition state, so I write a double dagger there. And as it's leaving, the CH2 is becoming delta plus. And the Br is taking both electrons of the bond and becoming delta minus. The bond that is dotted is breaking, and you indicate that in your transition state. And so if I were to draw the result to this, I get Br minus, and I get a carbocation. No surprises here. But in many ways, this looks like a primary carbocation. And remember, primary carbocations are not very stable. See, carbocations are stabilized by 3 factors. As we mentioned in class, those 3 factors are inductive electron donation. Carbons are better able to donate electrons through sigma bonds than hydrogens. So the more carbons you have attached to the C that has the positive, more stabilized. Hyperconjugation, carbons attached to the C plus have hydrogens that rotate past and can interact in a side-to-side manner to the empty 2p orbital. And steric assistance, because they're sp squared, the groups are further apart. All these factors help stabilize a carbocation, making tertiary carbocations the most stable and primary carbocations the least stable. So, this primary carbocation should be extremely unlikely to form, except for one important detail, and that is these pi electrons can move towards the positive charge. What is it called when you shift pi electrons? Well, that's called resonance. The primary carbocation in this case is resonance stabilized. Resonance stabilization is a very huge electronic stabilizing effect. The resonance structures A and B, let's label them A and B, don't exist. What exists is the resonance hybrid, where the pi bond is delocalized over all 3 atoms. The net result of this is the resonance hybrid. The pi bond extends right across, and the plus is smeared out over 2 carbons. The spreading out of the positive charge over many atoms stabilizes this molecule and has large impact on the reaction. So in actual fact, structures A and B don't exist. What exists is the resonance hybrid. Now, the stabilized resonance hybrid, as I stated, is quite stable. This is what the attacking nucleophile in step 2 will see. So when you actually carry out the second step and the nucleophile attacks, it can attack here or here. In this case, because the positions are symmetrical, you'll get the same molecule. So in step 2, if we were attacking, say, with a hydroxide or water molecule, we would produce an allylic alcohol. But the resonance stabilization allows the SN1 reaction to occur very rapidly. And as such, because the reaction occurs so rapidly, it often is faster than even tertiary alkyl halides. The nature of the resonance hybrid can also lead to unusual products. For example, if we take allylic halide that's not symmetrical, or does not, let me correct that, does not yield a symmetrical carbocation, you can actually form two products. So whenever you're doing SN1, as usual, it is very important you draw the carbocation. If I was not to draw the carbocation, I would simply draw the product, and I would say, if I'm treating this with water, say, solvolysis reaction, and it's going SN1, I get the carbocation, I'm going to substitute, the bromine's going to come off, I'll put an OH on, I would draw this as my only product. What you see here is a product alcohol formed by SN1 substitution of water for the bromine. However, I made a fatal error. I did not take the time to look at the carbocation. Draw the carbocation. The reason you were told to draw the carbocation is look for rearrangement. SN1 reactions will undergo 1,2 shifting if you can generate a more stable carbocation. Always remember, however, no carbocation is more stable than a resonance stabilized carbocation. I know that may not always be the case, but pretty much for this course it holds true. So here's my carbocation. Why did I have to draw it? I have to look for resonance stabilization. I can move those two pi electrons towards the positive charge and draw this resonance structure. Now, although resonance structures don't exist, they can give you good insight into site of attack. See, the incoming nucleophile will see positive charge wherever it appears on a resonance structure. So, not only does the positive appear here, but it also appears here in this resonance structure, which means the nucleophile could attack this position. Remember, resonance structures don't exist. What exists is the resonance hybrid. And so, this resonance contributor will cause this structure to also form. Now, you would not have predicted this structure if you did not take the time to draw the resonance stabilized carbocation. Also, you look for effects of resonance in shifting, and we covered some of this in the homework problems. So in fact, there are two products, two solutions to this. And although you would never be able to predict this, just so you can see what the product distribution, typically, you get about 56% in this reaction of but-2-ene 1-ol, okay, and 44% of but-3-ene 2-ol. Okay, so there you have it, SN1 with allylic. What about the case of the benzylic? Well, once again, SN1 with a benzylic halide. Benzylic halide will go through a similar transition state. Let's use Cl this time. Where in step 1, once again we have ionization, and you lose Cl in the transition state. You get a delta minus as you kick out the chlorine, delta plus on the CH2, you have a bond breaking. This is the slow step. Carbocation formation is the rate determining step in the SN1 reaction mechanism. So when you're done, you get a benzylic carbocation, CH2 positive, and you have a Cl minus. Now what's interesting is just like the allylic, the pi electrons in the neighboring aromatic group can shift towards the positive. I can take these 2 pi electrons, move them there. If I do that, I begin to move the positive charge around the ring. And if these pi electrons go there, move here. So here's the question. In the second step, the attack of the nucleophile, and let's use the same nucleophile we used as water, we now attack the resonance structure. Note that if I label structures A, B, C, D, and E, none of them exist. What exists is a combination of A, B, C, D, and E. What is called the resonance hybrid. What would that look like? Resonance hybrid would look like this. You see, Lewis structures demand that bonds exist between atoms. But in this case, we have delocalization spreading these pi electrons over all the carbons. So you end up with a delta plus here, a delta plus here, a delta plus here, a delta plus here. If you look at this, this suggests that you could get nucleophilic attack at any of the positions. However, take structure D. What would happen if a nucleophile came in and bonded to the positive charge in D? That is, I got an OH here. What would happen if this occurred? Well, you notice the ring pi system is now no longer an aromatic system. That is, the OH has disrupted the aromaticity of the ring. Aromatic rings are especially stable. They're stabilized and low energy. Because of this, such disruption is high energy and won't occur. So substitution at the positive charges found in resonance contributors B, C, and D does not occur because it would permanently disrupt aromaticity. Okay. That leaves structures A and E, and structures A and E are essentially the same thing. They're just resonance structures where you've shifted the pi bonds around the aromatic ring. Substitution at the positive charge on the CH2 generates the same molecule. And so if we did that and treated this with, say, H2O in the second step, I'm not going to draw, of course, the transition state there. You can look back at the SN1 mechanism and look at the deprotonation steps and the transition states. We would produce benzyl alcohol. This resonance stabilization in the SN1 makes benzylic and allylic halides overall more reactive than other halides. The trend in reactivity parallels the trend in carbocation stabilization. That is, if I was to write down a trend for carbocation stability, even with inductive electron donation, hyperconjugation, and steric assistance, tertiaries are less stable than allylic and benzylics that have resonance. So, in our trend of stability, benzylic, and I'll write allylic, both of them together, because they're both resonance stabilized, are more stable than tertiary. which are more stable than secondary, which are more stable than primary and methyl. Note, primary and methyl, if they show a reaction, are probably going SN2. In other words, the SN1 path is so high energy in this case for alkyl halides that the SN1 doesn't occur. So this also is the relative rates for SN1. Okay, so that's the SN1. But I did indicate that benzylics and allylics were also very effective at the SN2 reaction mechanism. That is, benzylic and allylics that are primary and secondary, not tertiary. So we have to explain that. How could benzylic and allylic be effective or also favor the SN2 if they favor the SN1 because of resonance? So let's take a look at the SN2 reaction mechanism. And we'll start with the allylic halide first. Now, suppose I have a simple allylic halide. And let's make it asymmetric. Let's actually put a CH3 here. And we've got Cl. There we go. So here is an allylic halide. And we're going to do SN2 with hydroxide. So SN2 and our nucleophiles hydroxide. Now if you remember, the SN2 is a one-step concerted process involving nucleophilic backside attack at the carbon bearing the halogen. So we have to look at this, and let's take a look at the transition state. In the transition state, when backside attack occurs, the carbon and the two hydrogens off the carbon that has the chlorine will be in a trigonal plane. The chlorine will be departing and the carbon will have achieved or rehybridized to an sp squared. And these other carbons are sp squared, so let's just take a look at this if we can. So I'm going to draw this. I'm going to put this CH3 down here. Okay, so here's a CH3. And over here I'm going to have an H. And I'm going to draw, and let's do our orbitals in red. We'll draw them in a moment. I'm going to draw sp squared. I'm going to show the pi bond here. And I'll put this H coming out here at an angle so it doesn't interfere with the other pi bond. And I'll put this guy here. And it has a couple of H's that lie in a trigonal plane. So there they are. And I'm going to draw in the 2p orbitals in red. Even with my limited artistry. So these are 2p orbitals. This one, of course, is our pi bond. Pi component of the double bond. This part of the molecule right here. And this guy's got an sp squared because you have a chlorine departing. So I'm indicating that this is my leaving group. And we have a hydroxide attacking here, coming in. So this is my transition state. There we go. And I have to show charge. The hydroxide, as the bond is forming to carbon, is losing its negative, so he's becoming delta minus. And the chlorine's taking both electrons of its carbon-chlorine bond, so as it leaves, it's becoming negative, so it's now delta minus. We have a bond forming, and we have a bond breaking. Now, an interesting point about this transition state. There is no resonance here, but we are familiar with the capability of 2p orbitals having side-to-side overlap. That is, the 2p orbitals here are making a pi bond. What's interesting to note, I'm going to write about this bond forming, is that side-to-side overlap interaction also occurs with the 2p orbital here. There is a side-to-side interaction. Now, think about the orbital that has the chlorine and the hydroxide competing for it. That means there's an awful lot of electron density being pumped into this system. It's a high energy state. Transition states are very high energy. Anything that can help stabilize this transition state, help delocalize that high charge of electron density, will stabilize the transition state. Side-to-side overlap allows electron movement along here. Okay, along here, throughout this pi system. That means this transition state is especially stabilized, and because of that special stabilization, the transition state, special stabilization in the transition state, the allylic transition state is low energy and more reactive often than even methyl halides. And so allylic become very reactive due to this extra stabilization, or the overlap of the side-to-side overlap of the 2p orbitals. But there's another direct consequence to this. If electron density can move through these side-to-side overlap pi systems, yes, this one will lead to this alcohol. But wouldn't it be possible then for the OH to come in here? If electrons can shift through the pi system, then couldn't the OH come here and the electrons move through the pi system? And as this happens, couldn't the pi bond relocate its position? So as the chlorine leaves, the pi bond now moved to this position. And this pi be the pi that's stabilized in the transition state, where this bond is breaking and this bond is forming. Well, if this does happen, if that happened, you would get this product. Wait a second, I've seen these products before. They're the same products we got because of resonance in the allylic case. Is that what's going on here? Is this resonance? Not really. In the transition state, you might say that yes, the electrons are delocalizing, and this is very similar to what happens in the resonance hybrid. But this happens in a transition state, whereas we represented the others as resonance. And because of that, we keep them or describe them as being different. No, this is occurring because the side-to-side overlap of the 2p orbitals allow electrons to delocalize. In principle, it is the same thing as resonance. But it helps if you keep these two ideas separate. And so actually, this attack at the different position is given a different mechanistic name. For allylics, it's called the SN2 prime. So when the OH leads to this, you got the SN2 prime. When it leads to the other one, you have the SN2 mechanism. Okay, so the side-to-side overlap in the transition state stabilizes the transition state, lowering the energy of the transition state. This speeds up the reaction, allowing allylics to be even faster than methyl halides. What about the benzylic case? Well, if we look at the transition state for the benzylic case, we get the same thing. Here is my benzylic CH2 chloride. We're going to do an SN2. And we're going to hit this with hydroxide. And we can draw, I'll sort of draw an edge on view if I can. We can draw the 2p orbitals that we would incur. In our transition state. And so if I do that in red again, just select a red, draw my 2p's, make them a little smaller so I can fit them all in. These are the 2p orbitals around the aromatic ring. And this is where we have our delocalization for our pi systems right around our ring. And this guy, I made him a little bigger than the other one, can side to side delocalize into it, which means that when we have our leaving group, which is the chloride, Cl, taking both electrons, starting to get negative, and the hydroxide is coming in. So this is a transition state. I've shown my delta minus. I can say bond forming. Draw my transition state, bond breaking. There we go. So we get this transition state. The transition state 2p orbital can delocalize the excess electron density into the aromatic ring. This delocalization is stabilizing. Stabilizing transition state lowers energy. Reaction speeds up. Benzylics react even faster than methyl halides, or can react faster than methyl halides. Net result of this is in the SN2 reaction of the benzylic, you end up substituting for the halide, and you produce benzyl alcohol. Now, here's a question. Can we get anything like the SN2 prime happening here? If we look at all these pi orbitals, these 2p orbitals, these pi bonds, can't we attack one of these 2p orbitals and do something like the SN2 prime? And the answer is no. Once again, just as we saw in the SN1, if hydroxide attacked any of these 2p orbitals, the OH would bind on the ring, disrupting the circular pi bonds. And the circular pi bonds are required for aromaticity, and aromatic rings are especially stable. So this would be too high energy. So in the benzylic case, it's a lot nicer. You don't have this problem with disruption of aromaticity, and you don't have to watch for that. However, because both transition states are more stabilized, once again, if we take a look at the relative rates, just as we did in the SN1, relative rates for the SN2, we find that the benzylic and the allylic react faster than the fastest alkyl halide for the SN2, which is methyl, who is faster than primary, who's faster than secondary, who's much faster than tertiary, because in fact tertiary, once again, tertiary would not even go SN1. If it reacted, it would probably go, it would not go SN2. If it reacted, it would probably go SN1. Okay. So there you have it. Allylic and benzylic halides under SN1 and SN2 reaction conditions. And now I'd like to give you just some final facts concerning the SN1 and SN2 reactions. Conditions are often designed to maximize yields, and it's important sometimes to drive a reaction to completion. One of the tricks used in this to prevent back reactions is to remove the leaving group remove the leaving group from the system by precipitation. This can be done by several ways, several different methodologies. In the SN2, we can use a nucleophile which is soluble, such as potassium iodide and acetone. We often use aprotic solvents and under SN2 conditions. Potassium iodide is soluble. The product, of course, in nucleophilic substitution and backside attack would be ethyl iodide. What's interesting, however, is potassium bromide is not acetone soluble, and so it removes itself from the system by precipitation. Likewise, we can use or help facilitate the removal of halogen under SN1 conditions by adding to a sulfolysis reaction, water or ethanol. We could add silver nitrate, and the silver halide would precipitate. So if I'm doing, for example, tertiary bromide, butyl bromide, with, say, water or ethanol. Let's try ethanol, okay, as my nucleophile. And ethanol is also my solvent, so it's a sulfolysis reaction. I might throw in something like silver nitrate. The reason for this is once the halide leaves, the bromide minus leaves, it combines with silver plus, and silver halides typically are insoluble. And so the resultant product, butyl ethyl ether, will form. And you can then have removed your bromine as silver bromide solid. So the KBr and silver bromide would precipitate out of solution as solids. The arrow down just simply means precipitate. Often it's just written as solid. Sometimes you see these arrows, sometimes you don't. Now, although we're talking about halide chemistry, I do want you to realize that many of the rules we've given apply to halides. Changing leaving groups can have a profound effect on the relative rates of reaction and can even influence the mechanism followed by a reaction. We learned last semester in alcohol chemistry that you can produce inorganic esters of alcohols. For example, you can produce molecules like methyl hydrogen sulfate. Methyl hydrogen sulfate. If you hit sulfuric acid with 2 equivalents of methanol at low temperatures, you can make dimethyl sulfate. The point is that the sulfate group is an excellent leaving group. You see, the sulfate group is the hydrogen sulfate or methyl sulfate group is derived from sulfuric acid. Sulfuric acid is a very powerful acid, so sulfate's a very weak base. Weak bases are very good leaving groups. So if you hit this molecule with a strong nucleophile like cyanide minus, you're clearly going to go SN2 and kick out the very good leaving group, in this case hydrogen sulfate, and in this case methyl sulfate. So if we use, I don't know, CH3, CH2, CH2, O minus as my nucleophile here, and it attacks. In these reactions, you'd get methyl cyanide here, plus HSO4 minus, or HLSO3 minus, same thing. And here you would get propyl-methyl ether or methyl-propyl ether. And this one you'd have methyl sulfate as your leaving group. Now what's interesting about the sulfate leaving groups is they're so good. You may recall in alkyl halides you were told that secondaries can go either SN1 or SN2. They go slowly, and you have to look at the strength of the nucleophile to try and determine whether it's going to favor SN1 over SN2 under reaction conditions. With these really excellent leaving groups, the SN2 is often favored for secondaries. Now another acid which leads to a conjugate base that is an excellent leaving group are the sulfonic acids. And these are, remember, benzene, sulfonic, acid, and this guy is para-toluene, sulfonic, acid. So benzene sulfonic acid and para-toluene sulfonic acid. Now what's interesting is these are derivatives. If you do the same thing, replace the H with a methyl group. In the benzene sulfonate case, so you have methyl benzene sulfonate. If you take methyl benzene sulfonate and you hit it with a powerful nucleophile like ethoxide, CH3CH2O-, or even a weak nucleophile, you're going to do an SN2 backside attack. You'll get ethyl methyl ether, and you'll get the sulfonate anion. Now, benzene sulfonic acid is a powerful acid. Because of that, its conjugate base, sulfonate, is a weak base, an excellent leaving group. Likewise, para-toluene sulfonate does the same thing. If I had a methyl here, I would have gotten the leaving group as para-toluene sulfonate, which is a weak base. Okay, so modifying the leaving group will change relative rates and sometimes even affect the nature of the mechanisms for secondaries, which can go either. And so the nature of the leaving group can actually influence the mechanistic pathway. All right. Well, that's it for this Scribblecast lecture. I thank you for listening. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you very much.